For the second talk, we're happy to have Benjamin Muntz, who will tell us about the geometry of gravitational effective field theories. Please start.
Okay, let's see if this works then. Thank you, Filippo and Bruno, for inviting me to give this talk. So today I'll tell you about a paper that came out back in December in collaboration with Sotirios Kalamitsos from Tartu in Estonia. And it's in general about geometry of gravitational effective field theories and trying to understand the situation there. So here's the plan. First, I'll tell you a bit about field space geometry, sort of vaguely why we want to consider this. Then I'll tell you about a puzzle. I'll tell you how to solve this puzzle using this framework that we call frame-augmented field space. And then I'll tell you how to use it, say, in a swampland context. I'll tell you about the species-scale distance conjecture and Sharpened distance conjecture. Cool. So also at any point, feel free to interrupt if you have any questions. So let me just start. So the topic of this talk is geometry of field space, and to introduce where this might show up, you have some effective field theory, maybe with a scalar sector, and you can stare at the kinetic term and see that it reminds you a lot of the line element that you would see in sort of everyday general relativity. And so the kinetic function that sits in front of the derivatives, d phi, looks very much like a metric term, and so you can very easily motivate like that this kinetic function gives rise to a metric on the field space manifold. So sort of heuristically, we can say that the f's are like points in this manifold, perturbations are like the tangent vectors, but we can also say something slightly more interesting just at a first glance, that if we want to do something like canonical normalization, there's to leading order, we just normalize the fields, then what this will do is really go to Riemann normal coordinates. So we can say something interesting, namely that if we have derivative interactions in this theory, then it's really an indicator that the field space is curved. So you can say some quite interesting statements just from looking at this picture. And so in string theory and swampland, we've spent a long time talking about field space, or in more particular the geometry of the moduli space. But this has been talked about in a bunch of other fields as well, and I just want to flash this real quick. So of course we want to talk about it maybe because we're interested in things like the distance conjecture, and there we need to have a metric on the moduli space. But also in a bunch of other areas in theoretical physics, people have gotten interested in studying the geometry of this field space. And due to time, I won't be going into all of them, but this is just to show that there are many ways to approach this problem and many motivations for it, and we can also try to learn from each other. But sort of broadly shared between all of these is there's a question mark missing, namely what happens when we couple the theory to gravity, and strange things starts to happen there, and this of course is a motto that we know and love from swampland as well, that gravity somehow does something special. And what happens is that when you couple to gravity, now we can perform, now the theory admits different descriptions related by Weyl transformations. So I can take my field space metric G mu and do a transformation where I scale it by some positive function omega squared. And so we can cast our theory in what we call different conformal frames. Here are, for example, two of them, but there's an infinite number of them that we could choose from. Maybe most familiar is what we call the Einstein frame, where the effective gravitational coupling is a constant. And then Jordan frame, maybe here's what I would call the Jordan frame is where the kinetic terms completely go away, but the kinetics of the scalar field is sort of hidden away inside this non-minimal coupling, which I call F. And so if you stare at the two actions and you read off what this field space metric is, Gij, you notice that they give different results. In Einstein frame, we get some general positive function, but in the Jordan frame, it's completely vanishing. And so this leads to a question. If we want to employ field space geometry for all of these different topics that I showed you on the previous slide, then which metric should we use? All of these geometries are clearly not the same, although different conformal frames are meant to describe the exact same physics. So how should we understand this transformation when moving between different frames of how the field space metric transforms? Cool. So this is the puzzle that I want to lay out. And let me zoom in on this statement that meant to describe the exact same physics. So this is, of course, a really important statement, and so let me elaborate. That if I have some quantity that I want to measure in my theory, could be a mass or coupling or whatever, so here I have very generally Q and it has some mass dimension. If I perform a Weyl transformation, then this quantity will be rescaled. But in physics, we never measure quantities themselves. We only measure dimensionless things, dimensionless ratios. And so really what we have to do is take a ratio of things, maybe some choice of ruler, and construct some dimensionless quantity pi, which we can measure. And if I perform a Weyl transformation, then the Q's will rescale, and it will look like the dimensionless quantity also rescales. But here's the catch. This is purely a fact. This is purely due to the fact that we have insisted on using the same ruler before and after performing a Weyl transformation. If you do a combined Weyl transformation and a unit transformation, so you also rescale your choice of ruler, then all dimensionless quantities are left the same. Okay, so this is why we mean that different conformal frames give you the exact same physics, because they give you the exact same dimensionless observables, provided we make the same the appropriate unit transformation. Okay. So a good analogy that I always want to throw out there is like in gauge theory. So in gauge theory, as you may know, we never measure absolute angles of fields. If I perform, if I want to say measure a phase difference, and I perform a U1 gauge transformation, say I rotate one field, then the phase difference is only going to look different if I insist on using the same reference angle. However, I should also U1 transform the reference angle, and then the phase difference will look exactly the same. So in fact, there's a very deep correspondence between these two things. So this so-called frame problem of whether Jordan-Einstein frame, all of these infinite number of frames are equivalent, this has been discussed for many years, but really the issue was already sort of picked out by Dickey back in the 60s. Namely, he noticed that, or argued that if I'm in Einstein frame and I work in, say, Planck units, then I'm going to get exactly the same dimensionless observables if I worked in Jordan frame in units of this non-minimal coupling, which is not a constant. So this is really, so let me be very clear. There is no frame problem. All conformal frames are exactly the same physically, provided that one makes the correct unit transformation when comparing dimensionless observables between different frames. Okay. So just to summarize, conformal frames are meant to give you the same dimensionless observables, provided we make the same unit, the appropriate unit transformation. But there's still this question of gravity, namely that if I have the field space metric, this is the only thing that doesn't transform by just an overall scale factor. There are additional terms due to how the theory couples to gravity. And so the question is, how do we unpack or try to deduce what is going on here? Okay, so this is the solution that we came up with. Just don't pick a frame yet, okay? So perform a Weyl transformation, but what you can do is just treat this factor omega, the conformal mode, as if it was a scalar field itself. And in that sense, we've not really chosen a conformal frame yet. So let's promote it to a scalar field, just temporarily. And in fact, it turns out to be convenient to work in terms of the log of the conformal factor. So we'll call that small omega. And later I'll identify it with the dilaton. And now this gives rise to a new geometry, one dimension higher, that's spanned by the conformal mode and the original set of scalars that we had. And this comes equipped with a well-defined covariant metric, where I use the indices capital Ij to denote the indices. And this is uniquely defined provided I know what the non-minimal coupling and the original kinetic, the kinetic term is in a particular frame. Then I can define this frame-augmented field space metric. And it transforms covariantly. So if I perform another Weyl transformation, I don't get all of these extra factors, in a sense, because I've already, by promoting the conformal mode to a scalar field, I've already performed a Weyl transformation. So doing another one doesn't really change a lot. And by doing this trick, you can notice something very cute. Namely, that if I want to go to a particular conformal frame, what I'm essentially doing is choosing my omega, my conformal mode, to be a function of the remaining scalar fields. And what this looks like in this augmented field space is that I'm selecting a codimension 1 submanifold. And the field space metric in a particular frame is that of the induced metric on that hypersurface. Okay, so here I have two examples, again, going back to Einstein frame and Jordan frame. But let me just mention briefly that this geometry turns out to be Lorentzian. So it's a well-known fact that the conformal mode shows up with the opposite sign in its kinetic term. And so this will act like a time-like direction in this augmented field space. And so now I can study what different frames are doing. So I can go back to my two examples here of Einstein frame and Jordan frame. And so Einstein frame is going to be defined by this implicit function here, where the effective gravitational coupling is equal to a constant, which I'll call ME, or the Einstein frame effective Planck mass, is some arbitrary constant. And there I can compute the induced field space metric, and I get the result that I would expect. Likewise, I can go to Jordan frame, and there I have a different implicit function, which gives me a different induced metric, which also agrees with what I would expect. Great. So this is sort of the general picture. You go to the augmented field space, and then you can choose any hypersurface. And for every hypersurface, there is an appropriate or a related conformal frame associated to it. But note that these constants here, ME and lambda, they're completely arbitrary. So I could choose for them to be whatever I want. And what this really corresponds to is, say for instance, lambda is equal to 1, or lambda is equal to 2. These are really just related by constant Weyl transformations. So say I multiplied every single scale in the universe by 2. And I think we can all appreciate that this would really not make any physical difference. And so therefore, I also want to make it clear that all of these different frames related by constant Weyl transformations are, in a sense, the same frame. There's not just one Einstein frame or one Jordan frame. There's really a continuum of Einstein frames. But the reason why we can make do with just considering one of them is because all of these this continuum of Einstein frames, they're all related by constant Weyl transformations. So picking a frame doesn't just pick a hypersurface, it actually picks out an entire foliation of this augmented field space. Foliation where all the leaves are related by constant Weyl, or here I've written scale transformations. Okay, so that's the general picture. So there are essentially two choices that one can make, and these are independent of one another. One is what frame that you pick, so you choose a hypersurface, and the second is what set of units you're working in. And these are two different choices. So when we talk about working in Einstein frame and in Planck units, really what we're saying is we're picking out a specific foliation. And Planck units just means that our ruler is whatever constant we chose in this implicit function here. Okay, the ratio is equal to 1. And so now we can make use of this foliation picture to make some nice differential geometric statements. For instance, mapping between Einstein and Jordan frame is really just a map between different leaves in a foliation, right? So maps from one hypersurface to another. And this can be applied, say, also to quantities like asking, oh, if I'm in Einstein frame and I'm working in Planck units, what unit should I be working in Jordan frame in order to get the same answers? So what do? I can't compare quantities from afar. So I take the effective gravitational coupling in Jordan frame and I pull it back to the Einstein frame, and I see that it's a non-nominal coupling agreeing with Dickey's observation. Okay, so one can play these kinds of games. In fact, because the conformal mode is a time-like direction, there's a very similar picture to what we usually do in, say, 3+1 decomposition in general relativity. And so one can apply things like the ADM formalism to understand these foliations. So to every conformal frame, there is an associated normal vector. We can compute the lapse, shift. In the paper, we show that, in fact, there's a unique frame where the shift vanishes, and this is the Einstein frame. And I'll show later as well why Einstein frame seems to be a bit special. And one can also ask how things vary along hypersurfaces by computing things like the induced covariant derivatives. So you can ask, for instance, say I have a dimensionless quantity and I want to figure out how it varies in a particular frame. Then I can compute the variation using the induced covariant derivative on that hypersurface, and this will transform covariantly under frame transformations. And I can do the same thing, in fact, also for dimension-full quantities. And here one has to define what in cosmology has been known for a long time. This is called a unit covariant derivative, but one can promote this idea to the frame augmented field space as well. And it essentially measures what is the physical rate of change of some dimension-full quantity up to the choice of unit, right? And again, alluding back to this this connection to gauge theory, you can see how this also very much looks like a gauge covariant derivative. Cool. So probably what most of us are interested in is how to compute, say, geodesics or geodesics distance for discussions of, say, swampland distance conjecture. And so one can ask now, okay, how do we compute geodesic distances in this picture? So a good ansatz would be to define distance as distance along some curve on a particular hypersurface, and then we use the induced field space metric to compute these distances. But there's a couple of reasons why this is not a very great ansatz. First of all, it's not obvious what happens in the case where this induced metric vanishes, and we saw an example of this earlier on in this talk. In general, if I would use this formula and compute the geodesic distance between two hypersurfaces, these would not even agree, and they would not even be covariant under frame transformations. So this seems to not be the correct approach. So what do? We go to the augmented field space point of view. So because the augmented field space metric is completely well-defined and covariant, we can define a geodesic distance there in the bulk, and then we can suppose we have some tangent vector of some curve. Then we can decompose the directional derivative of that tangent vector in terms of components along and normal to some hypersurface, arbitrary for now. But if the left-hand side vanishes, then we know that this is just a geodesic in the bulk. If then the extrinsic curvature also vanishes, then we have the directional derivative on that hypersurface sigma is also vanishing. And so V is both a geodesic, or sorry, I should say gamma is a geodesic, both in the bulk and on that hypersurface. So it's a totally geodesic hypersurface. And it turns out if you demand this thing that the extrinsic curvature vanishes, this turns out to be the Einstein frame that does this. And so this is the main catch, that geodesic distances computed in the augmented field space, geodesic distances, will agree with geodesics in the Einstein frame. And so our message sort of is that if you want to compute covariantly the geodesic distances in these sorts of field space geometries when coupled to gravity, really you should be doing it in the Einstein frame. Great. Any questions before I move on? No, awesome. So now let's try to apply some of this framework. So now I've laid it out. Now let's try to put it into some context. So first thing we want to consider is the species scale distance conjecture. And here I have sort of one short formulation of it. And so this is something that's been studied by many people in the audience. So I won't spend too much time motivating it. But essentially, one wants to study in string compactifications, say, the species scale and how it varies along moduli space. And to do this, we define the species vector, and the claim is that its norm is bounded by an upper bound and a lower bound. And this is with respect to the moduli space or field space metric. However, and this is not to attack the statement. In fact, I'm very sympathetic to it, but one can sort of nitpick and go into details and see that maybe certain things might want to be specified. For instance, this is clearly a unit-dependent statement. We have really, in the definition of the species vector, we need to define this ratio lambda species in terms of the d-dimensional Planck mass. And so one can ask, okay, first of all, this is dependent on your choice of units, but also why do we work in d-dimensional Planck units? In swampland context, we would generally expect the d-dimensional Planck mass to lie above lambda species. And also the philosopher Caspar Jacobs, he has a very nice paper also going through some of the heuristic motivation for why one might want to study why one might want to consider the d-dimensional Planck mass in the context of quantum gravity, and argues that some of these claims are maybe a bit untimely. And it's a bit odd that one would want to work in terms of a unit that generally sits above the cutoff. So why does it need to be this in general? And also, why this metric Gij, which one do we pick? We have one in Einstein frame, one in Jordan frame, so one would maybe want to specify which one it is. And so we wanted to unpack some of these questions. So to do this, we looked to compactifications, and we worked in general higher dimensional gravity theory, just of the following form. And we consider a very, very general compactification on the following product manifold. And so we have a lower dimensional dilaton and some volume moduli. And we just focus on the volume moduli for the sake of ease here. And so now when we compactify this theory down to lower small d dimensions, we obtain a field space which is governed by this dilaton omega and the radions phi, right? So it's very natural to associate here the dilaton omega, and that's why it's not a coincidence that we give it the same symbol. It's natural to associate the dilaton with the conformal mode previously, because excursions in omega are like performing lower dimensional Weyl transformations, right? And so one can compute the effective action, and one gets the following form here. And so let me try to unpack some of the terms here. So we have a volume factor, which is independent of the moduli. It's just these integrals. Then for the sake of ease later, I'm defining this pi here with a factor of d minus 2. Which is just a linear combination of the other fields. And so if I put on my scalar-tensor theorist hat on for a minute, and I stare at this action, I'll say, aha, Einstein frame is when the prefactor is constant. So pi is equal to a constant. And so I can actually identify ME as being this combination here, proportional to the high dimensional Planck mass. And so this is the crucial point, that although here we've identified in the scalar-tensor theorist language, ME to be proportional to the high dimensional Planck mass, this is not what we usually in string theory call the d-dimensional Planck units, right? Because what do? So we define the d-dimensional Planck mass, the units that we typically work in, to be proportional to this physical or warp volume factor, which depends on the moduli. And so I can look at this effective Planck mass that I had previously and see that, aha, this is like setting omega, the dilaton, equal to 0. Okay, so again, in the language of a scalar-tensor theorist, I would actually think of this not really as the Einstein frame Planck mass, but actually the Jordan frame Planck mass when omega is equal to 0. Okay, so there's this mismatch here, and this is where semantics becomes a bit careful. So the catch is that for these kinds of compactifications, we would expect the species scale to coincide with the higher dimensional Planck mass. So plugging this into the definition of the species vector, actually we can rewrite it in this language of frame covariance, and we see that the species vector relates to how the Jordan frame Planck mass, how the unit covariant derivative acts on it. Okay, so the species vector, in a sense, in this context, measures how the Jordan frame Planck mass changes in Einstein frame.
Sorry, Benjamin, you have only a few minutes left.
Great, yeah, I'll finish up now. So to make a long story short, so we compute what this species vector is, and one can sort of puzzle around with how these foliations look, and there's a distinguished time-like direction. But essentially, if anyone has questions, I'll gladly explain. But essentially, we find that the species vector, the norm of it, turns out to be bounded, dependent on the causal nature of the Jordan frame within this geometry. Okay, and this is without talking about any species or any towers of states or anything. And we find that the norm of the species vector is we recover the usual bound, but the direction of the bound depends on whether the Jordan frame is a time-like null or space-like hypersurface. Okay, and we test this in scalar-tensor theory examples and also things like Kaluza-Klein theory, which is well known. Okay, I think with the interest of time, I'll just jump to the conclusion. And if people have any questions about the Sharpened distance conjecture or how this aligns with some of the swampland claims, I'll be happy to take any questions. Thank you.
Thank you for the nice talk. And does anybody have questions? Yes, Alvaro?
I have a couple of quick questions. So thanks for the talk, Benjamin. I was first wondering, like, I got a bit puzzled by the puzzle that you raised somehow, in the sense that, I mean, I agree that one can do all this like more general formulation, like introduce more like redundancies in your theory to then fix them and so on. But usually this is something that we do to get something more manifest, that it's something that when we describe the physics, we try to get rid of, right? Like, I mean, any redundancy, we want to get rid of it because indeed observables should not depend on it. And in this sense, I got a bit puzzled because my understanding is that in general, we always, to formulate swampland conjectures, indeed we work. I mean, this is stated usually, right? Like we work in Einstein frame and d-dimensional Planck units. I mean, all statements about masses becoming light in the distance conjecture, or like when we also were talking about these species vectors and so on, and defining the log derivative, it's always in Einstein frame and d-dimensional Planck units. So, I mean, yeah, I just got a bit confused by this. Like, why is it so? Let's say, why do you claim it is somehow so problematic to formulate things in this way? I mean, if at the end of the day, my understanding is that the result is telling you a good way to compute distances and scales and so on is in Einstein frame and Planck units. So.
Yes, okay. So do I understand your question is like why do different frames, why does the question of how things transform between frames seems to be relevant here? Is that how I understood your question?
Yeah, I mean, it's like in general, if I have some frame which is not Einstein frame and I want to do any swampland statement, what I would do is just do my transformation to go to Einstein frame, measure things in Planck units, and then I think my statements and so on are well defined. Is this not true? And if so, like
yeah, so I think that this is where things get a bit fiddly, and we have to keep tongue in cheek also because we don't really have good nomenclature to talk about say, Planck mass, but between different frames and how we compare things there. I guess the easiest way to see where things might diverge a bit is that we in string compactifications use a lot of different ansatz, right? And sometimes you have volume moduli that are like you have a Weyl factor that sits both in the external and the internal part, but you also have then you maybe go to a different set of field space coordinates, and you have a Weyl factor that only touches the internal part, right? And we can see from going to the augmented field space point of view that actually these bases of fields, they are adapted coordinates to different frames. So whether you talk about field excursions in one basis versus the other basis actually takes you in different directions. But of course, if you flatten everything, if you just say go to one frame, then you might lose some of this information. I don't know if that's...
Isn't the one that is relevant precisely the one in Einstein frame, and then Planck units, and I'm defining the dimensional Planck units as what I can measure in, let's say, if I have Minkowski asymptotics, low energy scattering of gravitons, or like just, I mean, even, for example, even if this is a scale that is above the species scale or whatever, I don't care in the sense that it's something that I can measure at arbitrary low energies as well, like as the coupling of the dimensional gravitons to other particles. So this is what confused me a little bit, but maybe we can also discuss later.
I think these are subtle points. I would maybe put it this way as well, that we seem to be recovering these bounds somehow. If that's a coincidence, I would love to know how it's a coincidence, right? Yeah.
Okay, thank you.
Any other questions? So if not, I have one, which may be a bit vague. So I don't know if there's anything to say about that. But usually one difficulty that people have when dealing, for example, with a distance conjecture is that if when you introduce a potential, then trajectories are longer geodesics and nobody knows how to actually formulate a well-defined notion of distance. Can this formalism help in any way? If you have a theory with a scalar potential, for example, can you rephrase things in a different way?
Yeah, so this is a really good question, and something I've thought about as well. So in my first slide, I mentioned, I had on the screen how so when you have scalar subject to a potential, it is possible to define a geometry where that potential is encoded into it. This procedure is known as an Eisenhardt-Lift. And so something that I am thinking about now is, whether you can use this Eisenhardt-Lift to also encode potentials into this geometry. So yeah, this is like I guess my answer is maybe, probably yes, you can do this. Yeah.
Okay, thanks. Any other questions? Well, if not, let me stop the recording, but yeah, people feel free to hang around if anybody wants to talk some more or ask anything else.